Hello, everyone. I'm Ki-Ahm Lee, who will be a chairman of today's seminar. And I'm happy to introduce Professor Soonsik Kwon, who is an expert at the dispersive equations. He got his PhD under guidance of the Professor Terence Tao at 2008. He worked at the Princeton University as an instructor during 2008 to 2010. Since 2010, he worked at the KAIST Daejeon, Seoul, Daejeon, Korea. Today, he's going to talk about pseudo-conformal blow-up solutions to the self-dual Chern-Simons-Schro equations. Please welcome Professor Kwon. Please.
Okay, yes, thank you for the nice introduction. And then also, thank you for the chair, the Professor Lee, for invitation, and also the organizing this nice, the opportunity to communicate during the Corona period. Okay, so I'm a bit nervous because this is my first time giving this type of the online talk. Okay. So today I'm going to discuss blow-up construction result, which is called the pseudo-conformal blow-up solution to some dispersive equation. Like one can think, so this is kind of the nonlinear Schrodinger equation. Okay, so if you are familiar with many results in the nonlinear Schrodinger equations, then probably this talk would be easier. But if you are not familiar with that, then so since I know that there are many people are not from the dispersive area, so I'm going to spend quite a time to introduce the result on nonlinear Schrodinger equations. Okay, so the equation, the title is quite long. It's a Chern-Simons-Schrodinger. Okay, so this is a coupled equation, Chern-Simons field theory, and also some Schrodinger dynamics, and also it is some special case, self-dual case. Okay, so I'm going to explain what it means on the way. Okay, and this is a collaboration with my PhD student Ki-Ahm Kim. He's still on the graduate students, and then we will be on marketing in next year. Okay, so for the outline, okay, first I'm introducing the equation. Okay, so the equation is not very the old one. It's a pretty new model. It is derived in 1990. So by the Jack Q and P, so they are physicists. Okay, and from the study of the low dimensional physics, they use the Chern-Simons field theory to describe some dynamics of magnetism. So more precisely, they try to they explain some a quantum Hall effect. Okay, so but before their time, the Chern-Simons theory was already introduced by the Chern and Simon in 1970. They are kind of gauge invariant theory for the three-dimensional. Okay, but you can recall Yang-Mills theory is four-dimensional the gauge field theory. Okay, but so since the Chern-Simons theory is three dimensions, so including the time, so the space-time is three dimensions now. So in order to describe dynamics for the planar, on the plane, so the Chern-Simons the field theory was useful. So they in their Lagrangian the action, they included the Chern-Simons term in their model. Okay, so that's how we call it is a Chern-Simons of something. Okay, so there are not some other Chern-Simons models like a Chern-Simons-Higgs equation or the Chern-Simons-Maxwell. So they are all some kind of the wave equations, but here the Chern-Simons-Schrodinger is kind of gauge some nonlinear Schrodinger equation, but with the gauge field. Okay, so since I'm not like an expert on the gauge field theory. So now let me move quickly. So originally, you can just remember that this is originally given by some covariant the formulation. Okay. Okay. So so since this is gauge invariant the equation, so we have to fix the gauge condition in order to fix the dynamics. Okay. So the easiest choice of the gauge condition is Coulomb gauge. Okay, so we're gonna choose a Coulomb gauge, and then that was like the original the gauge choice from the development of the model. Okay, so we impose Coulomb gauge condition here, and then we further impose some symmetry, so like which is called equivariant condition. Okay, so in fact, once we fix the Coulomb gauge, then by Diosava's law, we can express like the connection field A, A1, A2, A0, in terms of the phi is a complex valued function. Okay, and then because the space dimension is 2, right? So this is defined for fixed time. This is defined on R2, and then it takes the complex value from basically from R2 to like R2, right? So under for such a function, then we impose some sort of the like extended notion of the radial assumption. Okay, so if m is 0, then it is a radial function. But if m is integer, then when in the domain, when the point on the domain is rotated one time, then in the target manifold like R2, then it will take like m times, like to the counterclockwise or the opposite direction. Okay, so so in this equivalent answer, when n equals 0, then you can think this is kind of radial assumption. Okay, but we study a little bit more general cases like m equivalent cases. Okay, so m is called equivalent index. Okay, so under the Coulomb gauge condition and such an equivalent index, then the equation, full equation becomes like as this form. Okay, so you can observe that this is u is basically the radial function. Okay, so because and so the first the linear part is is m equivalent Laplacian. So this is the radial Laplacian part, and then the angular term, the second derivative, which comes from the equivalent the assumption, and then it contains several like nonlinear terms. Okay, so if you just forget a theta a0, then the nonlinear term is just cubic nonlinear terms with g is just a constant. Okay, so this is kind of like a cubic nonlinear Schrödinger equation, but with some other complicated terms. Okay, so such a complicated terms, a theta or a0, they are expressed by u. Okay, so the formula of the a0 a theta is as this form. Okay, so you can observe that a theta contains some integral and then u square. Okay, so for the first nonlinear terms, this is also cubic but contains some integral. Second one is a theta square times u. So since a theta is u square, so this is quintic nonlinear terms with integral, and then a0 is also contains a theta and then u square. So this is also quintic nonlinear terms. So basically, the equation is kind of cubic quintic nonlinear Schrödinger equations, but some of nonlinear terms contains integral from 0 to r or r to the infinity. So some containing some non-local nonlinearity. Okay, but okay, so this equation looks very very complicated, but remarkably, such an equation has a very nice structure. Okay, so it is pretty natural because the original derivation is very simple and geometric. Okay, so now let me introduce the Bogomolini operator. So this is one way to express the equation. Okay, so under the the Coulomb gauge condition, we can observe Hamiltonian structure of the equation. Okay, so the equation can be written as a Hamiltonian equation, and then here the Hamiltonian function is of this form. Okay, so when you use like a Bogomolini operator, then Hamiltonian functional is expressed in a much simpler way. Okay, so this Hamiltonian, the functional, if you just simply replace such a Bogomolini operator just by usual the derivative, then this energy functional is very close to the nonlinear energy functional of the nonlinear Schrödinger equation. Okay, and then the sign of the second term, the u to the 4, that depends on the choice of the parameter g. Okay. So when the g greater than 1, then the sign is negative. So energy functional is not positive definite, or g is negative, g is less than 1, then this is positive definite. So which means when g less than 1, in view of the energy functional, the equation looks like a defocusing nonlinear Schrödinger equation. Other cases, it is focusing the nonlinear Schrödinger equation. Okay, so I think the most interesting, probably for many reasons, interesting case is the case when g equal 1. So when there is no like u to the 4 terms. Okay, then energy functional is written by purely Bogomolini operator. But in terms of the Bogomolini operator, this is energy functional itself looks like a quadratic form. Okay, but don't forget that this Bogomolini operator is not a linear operator. This is actually nonlinear first order derivative operator because u is involved in the inside of the derivative. Okay, so in the defocusing case, when g less than 1, some global well-potence and scattering on the equivalence condition that is obtained by Baoping Lu and Paul Smith in 2006. Okay, so this is due to by following concentration compactness argument by Koenig and Mel. So when for the defocusing case, then like nonlinear Schrödinger equation, for all data, it is the scattering, the solution global and scatter. And then for the focusing cases, the data, the solution, whose mass below the ground state that I'm going to introduce slightly later, that the scattering is true. Okay, and then in our work, we fix g equal 1. Okay, self-dual cases. Okay. Okay, so then now let me start to explain what is the main benefit and the main importance of the self-dual case. Okay, so if a nonlinear functional, energy functional contains only like some derivative of the quadratic terms without something else, then by taking functional derivative, I mean from this expression of the energy functional, if you look at the Hamiltonian the equations, then such an equation is written as this form. Like so here, the d plus u is a nonlinear first order derivative, and then Lu star is adjoint of Lu, and then Lu is a linearized operator of d plus u. Okay, so I mean it looks complicated, but by using such a nonlinear formulation, then only in the self-dual case when g equal 1, such an equation is written as this simple compact form. Okay, so what is important here is usually when one look at the second order, like a nonlinear Schrödinger equation, second order nonlinear like a PDE, it contains Laplacian with some nonlinear terms, right? So then such a second order the differential operator, they cannot decomposed into like the product of the two first order operator, okay? But they usually in such a gauge field theory, the people call the sum equation is self-dual if second order equation is factorized into like a two first order operators. Okay, so that is a very important benefit over usual nonlinear Schrödinger equation to this one. Okay, so that's why our result they work well with the self-dual condition. Okay, so in fact such the Chern-Simons-Schrödinger equation on the equivalent it can be expressed in several different ways. We write a radial Laplacian with some nonlinear terms, or M equivalent Laplacian with some nonlinear terms. Okay, so the effect in the future analysis, we will have to use all three formulation of the equation, but actually they are the same, but different looking formulation. Okay, and then on the way the a theta or a0 is given by the function u. Okay, and also there is supposed to be AR, but AR equals 0. That is from like a gauge condition, Coulomb gauge condition. Okay. Okay, then now let me give some like elementary and then the fact regarding to that equation. Okay, so symmetry and conservation law and then the identities are very important ingredient of all of the work in the nonlinear Schrödinger equations, because nonlinear Schrödinger equations has many nice symmetry, and making use of such a symmetry is a very essential part of most of the work. And then even if the Chern-Simons-Schrödinger equation looks very complicated, then it shares many the symmetry with the nonlinear Schrödinger equations. Okay, so probably the natural one would be the phase rotation. Okay, so if UTR is a solution, I theta UTR is also solution, and then it has the scaling symmetry. Okay, and then in view of the scaling symmetry, you can observe that this is L2 critical equations. Okay, so and also in addition to the phase rotation and scaling, I think in this work the most important symmetry would be the pseudo-conformal symmetry. So this is a pretty like a unique feature in nonlinear in the Schrödinger equations. Okay, linear Schrödinger equation or the mass critical nonlinear Schrödinger equation. Okay, so main the benefit of CSS is the existence of pseudo-conformal the transform. Okay, so from the formula of the pseudo-conformal transform, you can observe that such a solution do not exist at t equals 0. It has to blow up at t equals 0 around when t approaching to 0. Okay, so that is called the pseudo-conformal blow solution. Okay, so and then the conservation laws, they are connected to the symmetry. The mass conservation is basically due to from phase rotation, and then it has a Hamiltonian formulation. So it has an energy conservation, and also it has a virial identity. So the first line of the virial identity is actually the result of the pseudo-conformal symmetry, and the second line is from the Hamiltonian structure and also like the scaling symmetry. Okay, so due to the existence of such a symmetry, the one can easily expect such existence of such identity. And also, this is also very important feature that this one can I think that equation shares many things with the nonlinear Schrödinger equations. Okay, so there are some Cauchy theory for this equation. Okay, so the Cauchy theory is developed usually without the equivariance condition. Okay, so by fixing certain gauge, Coulomb gauge or other gauge, the people like they developed some Cauchy like the local existence, local well-posedness problem, but in our cases, we assume some assumption, like equivalent assumption. But under the equivalent assumption, we did on Coulomb gauge and equivalence assumption, Cauchy theory is not that difficult. It is pretty elementary. Okay, so the result is included in the Liu and Smith papers, in their scattering papers. So, but we are going to only use this one. Okay, but up to the scaling regularity, for the general data, Cauchy theory is not settled down. Okay, it is only done like almost critical the regularity by very the high technique by the Liu-Smith term. Okay, then now let me introduce like a static solution. Okay, so in other words, this can be called a soliton solution. Okay, so this is a dynamical solution, and then as like nonlinear Schrödinger equation and many other nonlinear equation, it has a static solutions, and then the one can directly just find out some very element the fact of the static solution, and then also the find out the exact formula for the static solution. Okay, under the n equivalent condition. Okay, so the static solution is of this form. It has some degeneracy at r equals 0, the r to the n degeneracy, and then at r equal infinity, it decays as r to the negative n plus 2. Okay, so it has a polynomial decay. Okay, so that is one of the main difference from like nonlinear Schrödinger, mass critical nonlinear Schrödinger equation. Okay, so because this is like a static solution to the Chern-Simons-Schrödinger, if you take the pseudo-conformal transform for this static solution, you can immediately obtain explicit formula for the finite time blow solution. So that is called ST. Okay, and then it blows up at t equals 0. Okay, so its blow rate is 1/t. It just concentrate around the origin, and then phase is also the rapidly the rotating the ST approaching to 0. Okay, so okay, so we explicitly have one very the natural the finite time blow solution. Okay, and then the main goal of our work is to investigate some quantitative like analysis around such the pseudo-conformal blow solution like ST. Okay, so I mean in this work the answer of very first question regarding to like what happens around the pseudo-conformal blow solutions. So actually, to simplify, then we want to ask how generic is the pseudo-conformal blow solution. Okay, so ST is an exact solution, and then we just to like give some prescribed some asymptotic profile. Okay, so here asymptotic profile may require some sort of the assumption. Then we want to find out, we want to construct a blow solution adapted to such a prescribed asymptotic profile. Okay, so in fact, such a ST, this blow solution has a 0 asymptotic profile. Okay, but for given asymptotic profile, and then satisfying some assumption that we wanna construct some blow-up solution, and then also we wanna prove some kind of the property of such a blow-up solution, and then to see what happened around that the blow-up solution ST. Okay, so in fact the main result is in threefold, like actually the existence and uniqueness and instability of the constructed blow-up solutions. But in fact they are all connected, but they are proved in the same way. Okay? So now let me start with explain the statement. Okay, so G star is asymptotic profile, okay, and then satisfying certain assumption. Okay, so this assumption is a codimension 1 assumption on in the function class of an equivalent function class, we impose like codimension 1 assumption, like just one equation. Okay, then we can find out the blow-up solution. Okay, blow-up solution whose marginal asymptotic is Z star. Okay, so Z star is given, and then we construct like a solution UT, and then if you subtract like ST part, like a blow-up part, then the remainder is Z star. Okay, so this is the limit when t converging to 0 blow-up time. So in fact we construct UT and this one, and then also from the asymptotic profile that we also has to evolve like Z backward in time. Then actually we construct the dynamics of this form around the t equal 0. Okay, and then you can observe that so the only G star is given. Then from the G star, we by imposing some equation that we construct ZTR, and then T around 0, and then also the constructed of the blow profile. Okay, so that is the existence part, and then the uniqueness part. Okay, so basically say for given like a G star, the solution, the satisfying this asymptotic profile has to be unique in certain class, in this class. Okay? So if U1 and U2 are solution, whose asymptotic profile is G star, and then when the UT converging to the G star in this way, then U1 and U2 should be same. Okay. So actually, this says the solution constructed the previous theorem has to be unique. Okay, and then I think this is most important theorem and the central theorem of this work. In fact, we can also show at the same time the solution that we constructed is unstable. Okay, so that is not so generic in the neighborhood of the pseudo-conformal solution. Okay, so when Z star is given, then in fact we can construct a family of the solution. Okay, so the family of the one parameter family. So such a the parameter is eta. Right, so eta is ranging from 0 to like a small number eta star. Okay, then when eta equals 0, then it is a blow-up solution that we constructed before. Okay, but when eta is positive, then the solution do not blow up. It should scatter, but both and backward in time. So which means so eta is a very small number, right? But if eta is very small, then we construct the solution to U eta, which concentrate as like a pseudo-conformal blow-up solution up to the scale, the length scale eta, and then they just spread out again. Okay, it almost blow up, but do not go to the extreme, but the spread out again. Okay, so that is actually the behavior of solution to U eta. Okay, then if you take the limit of eta going to 0, then one can construct H1 the family of the continuous family up to eta equals 0. Okay, so that actually shows in particular, like such the block solution that we constructed is unstable, because in a neighborhood if there are some error, like some error to some like U eta directions, then the solution that cannot blow up, right? And also at the same time, so when we construct like a family of the U eta, then we observe rotational instability. So actually we observed some mechanism of the instability. I mean, actually the why that explains why the solution cannot be why such a solution cannot be stable. Okay, so more precisely, so when eta is strictly positive, then solution solution that concentrate up to the scale length eta, and then they spread out. But in a very short time of length eta, when if they do not finish to the blob, then they rotate, abruptly rotate by angle m+1 over m pi. Okay, so when eta is 0, this is pi. Okay, so the situation is like this. The solution, just the block solution is concentrating as like the pseudo-conformal block solution. They just blow at time 0, but without any rotation. Okay, but if eta is non-zero, strictly positive, then they blow up, they are concentrating up to scale eta, but abruptly they take a rotation of angle almost pi and then spread out again. Okay, so that this is the pretty. I mean, we think this is the very interesting phenomenon. Okay, and then also it is not quite clear. I mean, if some other like a natural model also enjoy the same type of the rotational like the instability, but there are I was told from my friend that there are some like the heuristic, like the expectation for the Yang-Mills equation. If the angular momentum is non-zero, is survive, then such a solution that do not blow up. But when they are concentrating, then if very small angular momentum, if there is a very small non-zero angular momentum, it has to make some the immediate rotation, but actually block the blow. Okay, so for this model, I mean, the whatever region, we are able to observe this phenomenon. Okay, so and then this is some explanation of our work, and then now in fact the motivation or like and then the result, they are all like related to earlier work of the mass critical NLS. Okay, so this is our main work. It's quite analogous, and the statement itself is analogous to the mass critical NLS. And then it has related to like the two works. So one is Brook and Wang in 1997. So it is a pretty the celebrated very first the block construction, and then the Mayer Raphael Seftel in 2013 for this nonlinear Schrödinger equation, mass critical nonlinear Schrödinger equation. Okay, so for this mass critical nonlinear Schrödinger equation, as like a static solution Q, it has a standing wave, but it has a rotation in time. Okay, so that is one of the difference, and also it has a ground state. Okay, so R is a ground state, and then it has a standing wave solution. And also, such a mass-critically integrated equation has a pseudo-conformal symmetry. So if you take a pseudo-conformal symmetry, then it has a pseudo-conformal block solution. Okay. So in a neighborhood of such a pseudo-conformal block solution, the Brugge and Wang have shown that for given asymptotic profile, there exists a block solution as like ST. Okay. So this is similar to existence part of our work. Okay. So so in fact, the main the philosophy of the phenomena is definitely that's very taken from the Daejeon argument or Daejeon insight. So in fact, the writing down the solution, the psi is a blow part plus the asymptotic part, and then they evolve asymptotic the asymptotic part by following the nonlinear integrated equation. And then this is blow part. And then asymptotic part is a kind of regular solution. Near the blow time, it just stay, I mean, the well spread out and the scattering solution, right? But blow solution is concentrated very, very small region. I mean, this blow part is concentrated very small region. But if you write down the solution, sum of two, the asymptotic part and the blow part, then one can expect that there are very strong decoupling in scale. Okay, so this is asymptotic part, this is blow part, but the one is concentrated in very small region, but the other is just spread out. So their interaction is very small, right? So that is what one expects, and then by observing such a expectation, and then they are able to shows that they are almost decoupled. So one can eventually shows the blow solution. Okay, but and then so far later, the 15 years later, the Mel, Raphael, Seftel, they have shown the instability of the Brugge and Wang solution. Okay, so in fact, they have constructed a family of the solution, the one parameter family, eta, and then when eta equals 0, which is like a block solution, like a Brugge and Wang solution, and then if eta is positive, then it has to scatter. If eta negative, it belongs to like a stable block regime, so it also blow up, but with a completely different blow rate as against the a pseudo-conformal block solution. Okay, so in our work we do not have this part when eta is negative, because we do not see stable block regime. Okay, so in their work, even if the result is to show just instability of the Brugge and Wang solution, the analysis is quite different from Brugge and Wang's. They have to use the modulation analysis, right? And then in our the construction is the text is similar with the Mea Raphael Seftel's argument. Okay, so then now, so since I don't have much time, then let me go a little faster. Okay, so the phenomena and like a result, there are many similarity also, and then there are many also many difference, and then one of the main the issues and difference is the difference of the linearized operator. Okay, so if you linearize that around Q or the analysis for the around R, then we can completely find out the generalized null space of the linearized operator for the okay. So this is for the analysis. It is done by Weinstein in 1982, and then for our work, by using the self-duality, we can solve the equation. We can completely describe what is a generalized null space. Okay, so because there are some kernels in the linearized operator, and then we and then also the another element in the generalized the null space, all those directions are very crucial when you choose like some answer for the blow-up. Okay, and also the self-duality. So NLS is not self-dual, but the CSS is self-dual. Okay, for this linearized operator, the can be written as as this form. Okay, I mean the second order linearized operator can be written as a can be factorized the two first order operator. Okay, so I use this fact is essentially used for our analysis. Okay, so let me make some comment of our the theorem. Okay, so now let me make some let me focus on like a main difference from like NLS. Okay, one of the difference is interaction of the dynamics Z, I mean asymptotic profile, and blow-up solution ST. Okay. Okay, you can recall that in our nonlinear equations, nonlinear terms contains some integral from 0 to infinity, r to the infinity, or the 0 to r. Okay, so because nonlinear terms has a long range integral, so even if the z is like a kind of like the scattering solution, it's just spread out. Because of such a long range the nonlinear terms, we cannot avoid such a strong interaction between the blow profile and Z. Okay, so in Brugge and Wang's work, or the Meyer, Raphael, Septes, they just evolve Z asymptotic profile part just by following NLS, but in our case, we have to significantly modify evolution of the Z. Okay, so it turns out that such a Z has to evolve by by some other the equivalence like equation. So actually, by some different equation. Okay, in order to absorb some effect between just the two such a two interaction. Okay, so so in fact there are like two main the effect because of such the strong interaction that we have to modify our dynamics to observe such a strong interaction. One is like evolution of Z, and then the other is rotation part. Okay. Okay. And also okay, so as I explained, one of the interesting like the feature is the instability the mechanism that is quite different from like that of NLS. Okay, so for the NLS, the instability, I mean, so actually the main origin of such a difference is from the structure of the like generalized null space of the linearized operator of LNLS and LQ. But because of the difference, we can in CSS, the instability is due to like a spatial rotation. Okay, and then for the when the eta is non-zero, then it has to take a such a the uniform angle of the spatial rotation. Okay, and then this feature has in some sense made the similarity with some other like the Schrödinger type equation, like the energy critical the Schrödinger equation. Sorry. Not Schrödinger equation, Schrödinger map, right? Okay, so I think I don't have time to discuss the status of the proof, and then in my opinion, this is already the too like technical to present in 45-minute talk. So, but let me go very quickly. So actually, we take the modulation analysis, then writing down the solution in terms of by introducing the parameter, phase parameter gamma t, and then scaling parameter lambda t, and then another the parameter bt, so which is responsible for the pseudo-conformal phase. And then also we fix one parameter eta, okay? When eta is a small number, but it is fixed, okay? So this gamma t, lambda t, bt, they are modulation parameters. So evolving in time, we impose some condition and then we fix such a parameter, okay? So because for u, the global solution, not global solution, the solution to u around the time 0 is given, then since we introduced the degree of freedom, then once we fix such a 3 parameter, then the marginal part, the epsilon is fixed, okay? Then to fix such a dynamic, so we can impose the 3 conditions, okay? So 2 conditions will be spent for the orthogonality condition. Orthogonality, the guarantee like a coercivity of the linearized operator to avoid like actually two condition is spent for to avoid like a kernel of the linearized operator, and then the third condition that will be used to simplify the equations. Okay, so in this formulation, that we can write down the equation in terms of the epsilon. Then equation for the epsilon is of this form. Equation of the epsilon of this one. Okay, but before doing that, we have to fix the dynamics of G already. Then the dynamics of G is chosen to minimize the interaction between the G and like epsilon, G and the Q, and then by using some sort of energy, Lyapunov the functional argument, and then in order to show that the epsilon is converging to 0, by solving this equation. Okay, so this explains how we give like like 3 conditions of to determine the group dynamics. Okay, and then introducing this Lyapunov functional, like energy functional with some additional term, which is called the virial terms, and then energy the Lyapunov virial the argument we can show that, and also by using the coercivity that we can show that under the bootstrap argument that we can show epsilon is going to 0. Then that shows the solution is converging to the decomposing into the block part and with the asymptotic marginal part. Okay. Okay. So yeah, this is so I'm sorry about the like amount of the slide. And in fact, this slide is prepared for the 60-minute talk, and but since I'm going to like the post my slide on the web, so yeah, I guess you can find the more the useful information here. I mean, among that I didn't discuss in within the talk. Okay. So, okay, so I'm maybe overrun. So let me stop here. Yeah.
Okay. Thank you, Professor Kwon. And do you have any questions? So you can click, raise your hand, or type something at the chat screen. And so I have some small question. Well, whenever you prescribe the limit profile like G star, then you have a uniqueness of the profiles under the certain class. So could you give me some idea how you get such uniqueness? Is it really like something like a uniqueness through the backward time, something like that? It looks very interesting.
The uniqueness of Z or the uniqueness
No. Well, when G star is, yeah. Well, that is the second statement of your theory.
Okay, I see. Yeah, like this one, right? Yes.
Yes.
Yeah. So in fact, so in the construction, so only G star is given.
Okay.
Yeah. And then, so we wanna construct the block solution whose marginal asymptotic is G star.
Yeah.
Right. So actually, we wanna say such a solution whose asymptotic profile is G star is unique in some sense. Okay, and then this is a precise statement of that. Okay, when G star is given, then but technically we need such a okay. So G star is what happens for the block time at time 0, right? But in order to claim the uniqueness, we need to close like two solutions. We need to assume the solution is close to like this dynamics, like the block part and then Z.
I see.
By this sense.
With that rate.
Yeah, and also this condition is also satisfied our constructed block solution, which means the constructed we construct a solution that already satisfies this one. So if there are two, then it has to be unique. So the main statement is this in particular part, right? The solution that we have constructed that is unique. So this is essential. This is quite necessary because in our proof, in fact, okay. So even if I stated the theorem from the existence, so if you look at the proof, then in the proof, we just construct a family U eta when U is positive. And then the U0 is obtained by taking limit eta going to 0. Okay. Yeah. And then we have to verify such a limit, and then U eta has to be a continuous, the continuous family up to eta equals 0. Then, because when we construct the U0, then in fact we have to use a compactness argument. So it do not say like a uniqueness of U0 from the construction part. That's why we separately need the uniqueness proof.
I see. Yeah. And then the other question is like somehow whenever you give G star, then you can construct such solutions, block solutions.
Yes.
And then do you try to classify G star?
Okay. So in fact, the G star, I mean, what we can show is so the G star has to satisfy assumption H. Okay. So here, if you look at the assumption H is somewhat weird, but just forget everything. Originally, M equivalent the solution has to degenerate at 0, R equals 0, like R to the N. Okay, but we assume the G star degenerate as R to the n plus 2. Okay,
I see.
so
Some of the possible possibility of G star will give you a lot of different phenomena with such degeneracy. Some, therefore, maybe it's a good idea to see what kind of G star is possible.
Okay. Yeah, it is a very good question. Yeah, but the very, I mean, good and important question to this direction. But so in fact, we didn't prove that such assumption H is necessary for existence of the solution. Okay, but actually, I mean, that is also one of the interesting questions. But I think so in the asymptotic the profile side, in order to obtain some like a Bloch solution, we need like a codimension 1 condition on the asymptotic profile.
I see.
Yeah. So the actually extra degenerate condition is nothing but a codimension 1 condition. Okay. So we are working on the function space, and then there is the codimension 1 asymptotic profile like a manifold, and then if the asymptotic profile belong to that codimension 1 space, then we can show the existence. And then the same question to the like forward construction, like initial data, is very interesting. So which means, so we have like a finite time Bloch solution like ST. Then now we want to look at the neighborhood, open neighborhood of ST. Okay. Then one can ask if such a ST solution, Bloch solution is stable or not, right? Then by choosing some point on the neighborhood of ST, then if the solution Bloch or not, that is a very important question. But what we are, I mean, actually, this is our like the work in progress. So I mean, this is a backward the construction. Given asymptotic profile, we construct the Bloch solution. But now we are looking at from the initial data. Okay, but in this equation, I think Bloch solution ST is not stable Bloch, but one can construct the codimension 1 manifold of the Bloch solution, which means even for the initial condition side, once we give just 1 condition, then we can make it Bloch as like ST. So that's how much we can say how much generate that we can say such a pseudo-conformal Bloch solution.
Okay.
Yeah.
And do you have any questions? So if you have a further question, you can raise your hand. Okay, so since there is no raised hand, let's give the thanks to speaker again. And we have a coffee break right after this meeting. So probably, well, Daniel sent an email to you so you can click and join us. Thank you. Daniel, do you have a comment?
No, thank you, Ki-Aam. Thank you, Soonkin. Thank you. See you all in the coffee break. I close the meeting now.
Great talk. Thank you.